Hello, this is Jack Jackson. This is the first of a few videos where we will be going over review exercises for Unit 2A, which is the first half or so of the discrete probability portion of this playlist. So these problems in this review are for my students to help them focus on what's going to be coming up on Practice Test 2A and Exam 2A. Of course, you should first work through all the graded homework sets online and work through these slides. I assume that you've done that already and that you're ready to go on and try these problems. So these review exercises go over what's in this playlist up to this point, and they are selected problems to help focus everyone on the material that's going to be on the practice test. In fact, these problems are matched pretty well with those on the practice test. So what we're going to have here is a list of problems. Each one will have a slide. You'll be asked to pause on each slide, work the problem yourself, and then go to the next slide, and then we'll go over the answer on that slide. So we'll be doing this for each one. This video will go over the first 5 of these problems. Okay, here's exercise 1. Fill in the blanks. The probability quantifies uncertainty by assigning a number in the interval blank. B. The probability of an event which cannot occur is blank. C. The probability of an event which is equally likely to occur or not occur is blank. D. The probability of an event which must occur is blank. And E. If the sample space S is finite, we can find the probability of an event E by fill in the blank. Go ahead and work this out now. Come back when you're done. Press pause now. Well, probability quantifies uncertainty by assigning a number in the interval 0 to 1 inclusive, which we can write this way, bracket 0, 1, bracket. The probability of an event which cannot occur is 0. The probability of an event which is equally likely to occur or not occur is 0.5, which equals 1/2, which equals 50%. So any of those 3 forms would have been a correct answer. The probability of an event which must occur is 1, or 100%. If the sample space S is finite, then we can find the probability of an event E by dividing the size of the event by the size of the sample space. In other words, probability of E equals the size of E divided by the size of S. Exercise 2. Consider the experiment of rolling a standard fair die and let X be the number of dots on the top face. For numerical answers here, enter exact values in a reduced fractional form. A. X is a fill in the blank. B. The probability that X equals 5 equals C. The probability that X is less than or equal to 4 equals, and D. The probability that X is a composite number equals blank. Press pause. Well, X is a random variable. Specifically, it's a discrete uniform random variable. I was looking for a random variable there. The probability that X equals 5 is 1/6. There's 1 5 on the die and 6 total faces, all equally likely. So the probability is 1/6 that you will roll a 5. The probability that X is less than 4 means the probability that you'll roll something less than 4. Well, this is less than or equal to 4. So that would be the numbers 1, 2, 3, 4. There are 4 of those and 6 total. So the probability is 4/6, which reduces to 2/3. The probability that X is a composite number, well, that's the probability that X is in the set 4, and 6 because those are the only two composite numbers. Remember, composite numbers are numbers with 3 or more factors. Those would be 4 and 6. Prime numbers only have 2 factors. That would be 2, 3, and 5. And 1 is neither prime nor composite. It only has 1 factor. At least as far as the numbers on the die go, those are the only possibilities. So, there are 2 composite numbers possible on the die out of 6 total. So the probability that you roll a composite number is 2/6, which reduces to 1/3. Exercise 3. Let x be a discrete random variable. PDF stands for, fill in the blank. The output for a PDF is always in the interval blank. The sum of the outputs for a discrete PDF is always blank. PDF of k equals blank. This is a probability statement. Rewrite that as a probability statement. E, describe the graph of a PDF for a discrete random variable. CDF stands for, fill in the blank. CDF of k equals blank, fill in the probability statement there. And H, describe the graph of a CDF for a discrete random variable. Press pause now. In this context, PDF stands for a probability density function. The output for a PDF is always in the interval 0 to 1, including 0 and 1 as possibilities. After all, the output is a probability. So, like all probabilities, it's in the interval 0 to 1. The sum of the outputs for a discrete PDF is always 1. Remember, everything on the output is a probability. The probabilities all must add up to 1 because the PDF is evaluated at all possible different values of the random variable. And they take up all possibilities in the sample space. PDF of k is the probability that x equals k. So the output of the PDF is the probability associated with that input value. Describe the graph of a PDF for a discrete random variable. Well, it's a vertical bar graph where the widths of the bars are the same and the height of the bar above x is the PDF of x, which is the probability of x. CDF stands for cumulative density function. CDF of k equals the probability that x is less than or equal to k. So for a finite distribution, a PDF is a lot like a relative frequency, and a CDF is a lot like a cumulative relative frequency. H, describe the graph of a CDF for a discrete random variable. It's a step function consisting of parts of horizontal lines. The ray on the left is at y equals 0, and the ray on the right is at y equals 1. Between these, the graph is a sequence of horizontal line segments closed on the right and open on the left. The breaks occur when the x value has a non-zero probability. And the amount of jumps in the vertical heights of these little line segments is the same as the heights of the bar on the PDF. We'll be dealing a lot more with PDFs and CDFs as we move into the second half of Unit 2 or Unit 2B. Exercise 4. In a particular statistics class, 60% of the students are female, 40% are health science majors, and 30% are female health science majors. Let F be the event a randomly selected student from this class is female, and H be the event that the student is a health science major. Enter the answers in percentage form for the following probabilities. A, P of F. B, P of H. C, P of F and H. D, P of F or H. And E, the probability that the student chosen is a male. Press pause now. Well, we were told that 60% of the students are female. That is a relative frequency, or proportion, and that's the same as the probability that a randomly chosen person from this group is part of that subgroup, in this case female. So the probability of a female is 60%. Probability of a health science major being chosen, similarly, is 40%. We were also told that 30% are both female and health science majors, so that's the probability of F and H. That could also be listed as the probability of F intersect H. The probability of F or H is the probability of F plus the probability of H minus the probability of F and H. So that's 0.6 plus 0.4 minus 0.3 is 0.7, which is 70%. Not female is male, so the probability of male is just the part that's not female. So it's 1 minus 0.6 or 0.4 or 40%. Exercise 5. Consider the experiment of randomly drawing a single card from a standard deck of cards. Give exact answers as integers or reduced fractions. A, the probability that you draw a numbered card. B, the probability that you draw a spade. C, the probability it's both a numbered card and a spade. D, the probability that it's a numbered card or a spade. E, the probability it's a numbered card given it's a spade. F, the probability that it's a spade given that it's a numbered card. And then G, the question is, are the events of drawing a spade and drawing a numbered card independent? Go ahead and work this one out now. Press pause. Well, let's see here. We want to draw a numbered card. Well, notice that there are 9 numbered cards within each suit. There's a 2, 3, 4, 5, 6, 7, 8, 9, and 10 of each of the 4 suits. Notice that an ace is kind of like a 1, but it actually doesn't have a number on it. It has an A. And then the others are called face cards. They don't have numbers on them either. So there is 9 times 4 is 36 over 52 is the probability. That reduces to 9/13. What about the probability of a spade? Well, 1/4 of all the cards are spades, so the probability is 1/4. As an unreduced fraction, that would be 13 over 52, reduces to 1/4. The probability that's a numbered card and a spade, well, let's see, there are 9 numbered cards which are spades, so that's 9 for the numerator and 52 for the denominator, so 9/52 is that probability. The probability that's a numbered card or a spade. Okay, let's think about this a minute. Let's first add up all the numbered cards. Let's see, we said there's 9 times 4, so there's 36 of those. And how many spades are not numbered cards? Well, the ace, king, queen, and jack. So there are 4 more spades that are not numbered cards. Add those to the 36 to get a total of 40. So this probability is 40 over 52, which reduces to 10/13. Notice that we need to be careful here when we're doing an OR probability or union probability that we count everything, including the overlap, but we only count it once. All right, so those are straight probabilities on these parts that we just did. The next 2 are conditional probabilities. What is the probability of a numbered card given that it's a spade? Well, when we do this, we restrict ourselves to just the spades. And there are 13 of those, 9 of which are numbered cards, so this is 9/13. What is the probability that it's a spade given it's a numbered card? Well, this time we limit ourselves to just the numbered cards, so that was 36 numbered cards, and of them 9 are spades, so that's an unreduced number fraction. That's 9/36. That reduces to 1/4. Are the events of drawing a spade and drawing a numbered card independent? Yes. because the probability of a spade equals the probability of a spade given that it's a numbered card. So remember that we have a set of independent events, or two events are independent of each other. If the probability of a spade and the probability of a spade given the number card are the same, we say that those are independent events. In this case, those are both 1/4. The probability of a spade is 1/4. Probability of a spade given it's a number card is also 1/4. So those are independent events. Come back for the next video to watch the next 5 exercises in this review set.